I hope this is recording. Okay, so what page is it? 137. So a car of mass m and a toy truck of mass 3m travel in opposite directions at identical speeds. The truck moves. It helps to like underline the important information in the questions. The truck moves to the right and the car moves to the left. Since there's right and left, we expect opposite direction, right? The two toys collide and stick together. Before we even look at any questions, if they collide and stick together, in which direction will the whole system move after they've collided? To the right. Yep. Because the truck is bigger, right? Which of the two has larger initial momentum? The truck. Okay. Identify the system by drawing a dotted circle around the truck and the car. Okay. That is the system. Sorry? No. It is dotted.
Those are lines with spaces.
It is erased. Identify the system by drawing a dotted circle around the truck and the car. So the system is the truck and the car. Diagram the situation. The car has initial momentum. The initial momentum of the car is m times v. The labeling of these axes, never mind, m times v. So m times v, you can use, what do you want to use? Do you want to use this little thing, or do you want to use this thing? That's my momentum of the car. Oh, yes. Thank you. Because it's going to the left, right? Because left is negative, it goes under. The truck's initial momentum is positive. Take 3 of those. I hope you can see that on my scale, my little car has 2 unit squares, and my truck has 8 unit squares because this is 3 times the area of this one. Yeah, you can make your own, but on mine, this one is 3 times the area of this one.
They both have the same speed.
Yes.
So why is that one have so much more speed?
Because it has 3 times, no, momentum.
Whoa.
This is mass, my goodness. Oh, yeah. 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 Should be like that. Okay. Should be like this. Because it has 3 times the mass. And what's the final momentum of the system? What's the final momentum of the system? Yes. The final momentum has to be equal to the initial momentum. And the initial momentum is this plus this, or technically this minus that, which I'll just be left with this much, right? Yeah.
Is the final speed the same?
No, it's not the same. It can't be the same.
But you drew them as the same.
The final momentum.
The final speed.
We don't know the final speed.
But you put them as the same. But you said they're not the same.
Why are they not the same?
The final speed?
Yeah.
Do you expect the final speed to be bigger or smaller than the initial speed? Smaller, right? So,
Can I draw it like half height?
but you don't know what it is. That's the issue. But the area is the same.
The area should be.
The area is the same. Like this area minus that area is what I'm representing here. I don't know what the final speed is.
Yeah, so it doesn't matter what the final speed is as long as the area is the same.
Yeah.
I can make the speed less still.
Yeah. What is being looked for here is how many boxes do you have here? If you take away these many boxes, is that what you've represented here? Yes.
So let's say with the final mass has to be 4.
Of the system.
Yeah, it has to be 4. Well, okay, it has to be. Well, you did use here. See how there you put your first mass as 2.
Mm-hmm. So I'm just using
So
2
now
boxes to be 1
the
unit.
final thing is 4.
Mm-hmm.
So you take up 8 squares, the mass. That's why I think the height reduces to make the square. The speed reduces to make the square.
To what? The speed reduces to what?
That's okay. I don't know. The mass has to.
I know what you're saying.
Mass shrunk.
You're suggesting
Not 2. I don't know.
1, 2, 3, 4. Are you suggesting this?
8. But I don't know the speed. But I know the speed 8.
That's why I'm saying that what's going to matter is, because this is also correct. What we had initially is also correct.
But the mass is different. The mass is not the total mass.
I'm representing the area.
Yeah, but what about
on the graph?
The mass, because the way you drew it before, it means that the thing had a smaller mass.
That the system had a smaller mass?
Yeah. Oh, the way you drew it before, then the system had a smaller mass.
Yeah.
We're looking at the system as a whole. Mm-hmm. Exactly. The mass has to be represented.
Okay. Okay. So the mass is 4, right?
Yeah,
Maybe. Sorry? The total mass of the system is 4. Can you help me check what does the thing say? The solution thing.
What I'm saying, well, it doesn't. I haven't read down yet, just based on the boxes. I said it must be. It's drawing like what you do. But the mass, yeah, it's that plus that.
1, 2, 3, 1, 2, 3, 4. Okay, yeah. George is right. Are you a genius or are you a copycat?
George. Well, no, that's all. It doesn't tell me mass exactly.
Okay. So yeah, we're representing the total mass of the system as 4 units. In my thing, I'm using 2 boxes to represent 1 unit. Total mass of the system is 4, and the final speed is less than the initial speed. Yep. The boxes. You make your own scale and stick to the scale.
Yeah.
Yeah. Yep. The Torica and the track are now pressed together with an ideal spring compressed between them. You missed something?
Yeah.
What did we miss? In which direction will they be traveling after they collide? I thought we said that.
So we just need to the right?
Yeah. They're going to the right. Why are they going to the right?
Because the box on the left and the greater mass and they both have the same velocity.
Can you explain it in terms of momentum?
Oh, because the final momentum is positive.
Yeah. Do you guys all see that? Because this momentum will be I think it will be 3mv positive, and this momentum will be mv negative. I'm adding a negative value, so therefore the total initial momentum is 2mv, which is also equal to the total final momentum, so that means it's moving to the right. Yeah. Yes. To the right, momentum is positive. The toy car and truck are now pressed together with an ideal spring compressed between them. They are then released from rest. Diagram the momentum before and after the explosion, as well as the energy before and after the explosion. Sorry? How?
I don't understand what they're saying.
They're saying that they are, imagine this truck. How do you draw a truck? What a good truck. And a small car.
So it goes back in the direction.
There's a spring here, right? And they are compressed together. Remember, these are toys. and then the spring is released. So they shoot off in opposite directions. Yes, they start at rest. So they shoot off in opposite direction because this spring will be pushing most of them. So they're asking us to draw the momentum before and after the explosion, because this is an example of an explosion. So in the initial state, what is the momentum of the system? It is zero. Thank you. Because yeah, rest. And what's the mass?
It's 4 m stuff for your scale.
Oh, I'm just gonna go back to 1, 2, 3, 4, 5, 6, 7, 8. I can't even see these things anymore. What is the car's final momentum? The final momentum. This is the car. This is the truck.
Oh, with the truck doesn't move.
Yes. The car.
Positive.
It has a mass of 1.
Mm-hmm.
And it has a velocity of 3.
A velocity of 3. Yes, we can.
Does it matter as long as the car's final and the truck final momentum, if you add them together,
That's very important. So that's the first thing you realize, that when you add them together, they have to be zero, right? So it does matter, because what happens is you need to choose a value of velocity, because which one do you expect to have different velocity? Do you expect them to have the same velocity? No, this one will have a smaller velocity, this one will have a bigger velocity. But their momentas will be opposite and equal. So as long as you draw something that shows that this one's momentum added to this one's momentum gives you zero, you're fine. The mass of, yeah, the mass of each car. So the mass of the truck has to be 3, right? And the mass of the car.
So then if you know that, you know the velocity for the other one.
So 3, 4, 5, 6. And the mass of the car has to be 1. So which one is positive?
The
Car is positive. So I need to figure out what area to use here such that it's less than this one. Okay?
yes.
So if I give this a velocity of, wait, this is what? 3? 3, 6. So that's the velocity of 3.
Yeah, it needs to go up to 3.
1, 2, 3, 4, 5, 6. So that means this has a velocity of 3, and therefore this has a velocity of 1, right? So this will be 3 and 1 down here.
1 or 2 boxes.
no, 2. 2
Your scale is weird.
But this one is,
If it's 6, then that would be 2.
1, 2, 3. Yeah. I'm doing this scale for you because so that you can see it easier. Okay, is this diagram okay for everyone? Yes, you know? Yeah. What about the initial energy? Do we have kinetic energy initially? Do we have gravitational potential energy? Do we have elastic potential energy? Do we have any work done by external forces? So all the work is due to elastic potential energy, right? All the energy that's present is due to elastic potential energy. What about in the final state? What do we have in the final state? Question, this one? Again, choose your scale. Because if these are, I don't know how many these are, 1, 2, 3, 4, 5, 6, 7, then whatever you have this side must add up to 7. So, no, on the x-axis, you don't need anything. Because the x-axis doesn't have a unit. Yeah. Sorry? How big your block is on the x-axis. What matters is that whatever you have drawn here is the same as what you've drawn here.
It's only the white that matters.
Yes. Yep. Yes, it's an inelastic collision in part A, but in part whatever. But in part C, it's an explosion, and that explosion is coming from this spring being in the middle of the cars, and the spring has elastic potential energy. The words are confusing. Elastic potential energy is not the same as elastic collision. It's just energy due to a spring, right? So in the final state, what do we have? Yes, we have kinetic, right? But what kind of kinetic? Because we have kinetic of this track and we have kinetic of that track. How are we going to represent those two? Are we just going to draw one kinetic energy bar chart? Are we? Diagram the momentum before and after the explosion, as well as the energy before and after the explosion. I'm trying to see whether they require two or just one. Let's think of the meaning. If you draw just one kinetic energy thingy, what does that mean?
Yeah, it means they're together.
It means the energy of the system, right? What alternative can there be? I think you could also draw them separately to show the kinetic energy of the truck and the kinetic energy of the car. Which one do you expect to have a higher kinetic energy? Yeah, so which of the two quantities affects the energy more? Speed, right? So which one do you expect to have higher kinetic energy? The car. So I could draw this as car, and then maybe I can use another color for the truck, as long as to give you 7.
Do they have to be proportional?
I think
they do, right? Well, it has to be like the car to be, I don't know, 3 times greater than the truck.
Yeah.
Okay, so the left side.
Sorry?
The car has to be 3 times greater than the truck, right?
I don't think so. If the velocity is 9 times greater than the energy, if the velocity is 3 times greater, then the energy will be 9 times greater. But this is an energy bar chart, so honestly, as long as you draw them adding up.
What I'm saying here, I just cheated now.
Sorry?
I cheated now. And what I'm saying is, they draw proportion.
To the 1, 2, 3, 4, 5, 6. Huh.
Actually, yeah, because the kinetic energy is 3 times. The car has 3 times. So it goes V is 9, right?
Yeah, no. The velocity is 3 times, so the kinetic energy will be 9 times, right?
But the mass is not the same because the other mass is greater by 3. So
it's 3 times.
The difference between the kinetic energy is going to be a factor of 3.
Yeah, I don't think there would be that. I don't know. The answer says that, but I feel like it's a long stretch.
Are these going to be
the charts?
Yeah.
There have been some, but they're mostly for understanding.
So they're not straight.
I'm not saying there have never been any.
No, but they're not straight one direction. They're not too straight.
Yeah. It would be very. Okay, is this okay for everyone? Can we move on? Is it okay to move on? Yeah. This one? This part. The blue represents the kinetic energy of the car. It's a bigger bar because it has bigger speed. And the black represents the kinetic energy of the truck. But both of them together, their heights add up to the same height as we have that side. Like I told you, the x-axis of this graph is insignificant. It's only the height that matters.
But then that one has no boxes.
the x-axis doesn't matter.
So even if that one has more boxes than the other one, it doesn't matter.
Yeah.
As long as
Because it's not even labeled as anything. So it's the height that matters for this energy graph. Yeah. The height has to add up to that one.
you said you can draw one if you want, right?
Can draw what?
One chart, right?
There is no restriction in the question for drawing one chart. Because it says diagram the momentum before and after the explosion, as well as the energy before and after the explosion. It doesn't say of the two cars. So I think you'd be right if you did just one.
So then what did you choose to draw to?
Explanation. Yeah. I think that would be requiring too much of the student to draw them proportionately. As you know, as a teacher, if a student displayed this idea that one car has less energy than the other car, and they both add up to the same, as a teacher, they would earn the marks. To require them to show the proportionality between the energies, I think would be too much.
What I understand is what is does it matter that like in the explanation said that the car has a greater kinetic energy?
Sorry?
It says that the car has a
Good. Yeah, it does. Because from this explosion, you expect the car with a smaller mass to get a bigger speed, therefore bigger kinetic energy. Even if this has a bigger mass, the equation for kinetic energy is half mv squared. The speed contributes more to the energy than the mass does. Yeah.
So it's not proportional.
Sorry?
You said it was too much to the number of people.
Yes,
So
in my opinion. I bet, yeah.
Okay. Yeah, too much.
If there were instead two identical, yeah, imagine trying to figure out the proportionality. If there were instead two identical toy cars, so same mass, traveling in opposite directions at identical speeds, how would the momentum diagram change? And what direction would they be traveling after the collision? Explain and justify your answer. Okay, you guys are going to do this one, but let's first think about it. Okay? I'm not doing it.
But you said we're doing this in class.
Yes.
How did you say
Let's first like eat through it together, and then you'll know what you need to do, right? You have two identical cars, same mass, same speed, traveling towards each other. Identical mass, same speed, traveling towards each other. What's going to happen? Yes. Initial momentum is? What's the initial? Yes, it's also zero because they are the same momentum, but they're opposite.
on that thing
Yeah. Initial momentum of the system will be zero. Mass times, so yeah. One will be negative and one will be positive, but it will be the same thing. Look, I even drew it. Never mind. That's supposed to draw it. You guys do that one and then explain what happens. Oh, move on. Nice. Positive, negative. Yeah, that's it. Explanation. Hmm?
and explain why.
Because let me just preload the next one, which is supposed to be a homework. Sorry? Yeah. And it's page what?
There's one at 140.
140.
of the car bouncing back to the top speed.
Where is 140?
Imagine if this whole time we are already recording. Already, I sharing this screen.
No, I'm not. I'm not on Google something. I'm just doing old school recording. Is it this one? 140, you say?
Top speed, yeah, we missed. Yeah, there.
Okay. Let's discuss this one. Mike has already started on this one, so he can tell us what's up.
Mr. Williams stealing from what was the college board resources?
I'm not stealing. I don't steal these things.
You're just borrowing to use in class.
These guys know that we have screenshot tools. So
We know you have a...
screenshot tools.
So?
If they really didn't want us to do this, they should have specified.
No.
They should have specified.
They probably did.
You're not allowed to copy or redistribute without their approval.
So you're copying.
I am not redistributing.
To us,
No, we are allowed to use them for purposes of the classroom, which I am doing this for the purposes of the classroom, yes.
But by copying, you distribute.
I'm not distributing. It's not like I'm giving this to you. I'm not giving them to you.
No, but let's see this, right?
What's the difference between looking at this here and looking at it here?
Let's see, right? Let's say I buy a movie, right? I'm like,
Reggie, do you buy movies?
You don't know.
Be honest.
You're not allowed to like have like a lot of people come and watch it for free.
Yeah, you're not.
So it's the same thing.
Wait, what do you mean you're not allowed?
Copyright. There's a maximum number of people that can be watching the movie at the same time.
That's more like a school. You weren't allowed to watch movies.
Anyways, toy car is pushed with speed V towards the toy truck initially at rest. The car bounces back off the track, so the car's final speed is half in the opposite direction. Consider the system to be the car and the truck. Sketch the momentum diagram for the car and the truck before and after the collision. So the truck is at rest, that's the easy one. Its initial momentum is 0. Then draw the truck momentum as 0. The toy car has speed V. In which direction is it moving? Negative. So where is its area going to be? Sorry?
Like on the negative, but 1.
Yeah, on 1. And what's the car's final momentum?
Same mass, but half speed.
Half speed, and therefore the truck's final momentum?
Half.
In which direction? This is what you're thinking about. You're drawing the car's momentum initially with its respective direction, because car is negative initially. The truck initially is 0. The car finally is positive, but it's half the speed, right? And therefore the truck will be negative, and you need to figure out what proportion makes it equal to the cars so that it equals 0. Does that make sense? Yeah, because the initial momentum was 0. So Hudson, would you like to come show us what it would look like? No? What is the car's initial momentum? MB, right? Is it positive or negative? Negative, because moving left. So then you can, let me use this. And the truck's initial momentum is 0, right? The car loses speed. Its final momentum is positive, but its speed is a half. Yes? Or 3, you're right. I'm not saying you should use my scale. I'm just using this because it's very, if I draw a small one, it will be harder for you to see. Don't use my scale. Use your own scale.
Just do well, I'm using a pen, so don't.
Why do you use a pen?
If you do a pen, just.
Then don't copy me if you trust yourself.
Yeah, I know, but I can't trust them.
If you trust.
Only use pen if you're watching the recording.
If you trust yourself,
you still go back.
Don't copy me. Okay, let me use the scale you want. So I'm using 2 by 2 to represent 1, right? Okay. The torque is 0. Then I'll be using.
Are we using 2 by 2 or is it 2 by 4?
I think we would feel better if your messy sketch was outside the two. Now
V
it's
is
filled,
2.
but before it was filled. It
Okay.
looked like 1.7.
Cars in its final momentum is going to be that, right? And therefore, the truck's final momentum has to be something that adds up to this to give you 0. To give you that, sorry. So what's the truck's final momentum? And it has to be negative. Sorry? It doesn't give you 0, it gives you this.
Whoa! So it's final momentum and it's momentum.
Also, you can't really use any scale.
I would say think of it as number of, you see these little boxes? That's what you should use, guys. As long as you have the same little boxes, I wouldn't worry about the sizes of the M and the etc. Yes, but I wouldn't worry about it.
So you're saying yes?
On the representation, I wouldn't. Because, like in this case, how am I going to draw the 3M, 1, 2?
I've been trying and I found one where if you make the first one like this, but it takes so much time.
That's why I wouldn't stress it. 8, 4.
You can make it 6.
These ones.
You make the first line 6.
Yeah.
This is okay.
This is okay. This is okay. This is okay. This is how many? 1, 2, 3, 4, 5, 6, 7. Yes. What? Then this should be 8 also.
Wait, what? This is negative 4. And this is 2. And that's negative 6.
Now what I'm saying is this plus this must equal this. Because this is where all the momentum
yeah, that still makes sense. Negative 6 plus 2 equals to negative 1.
Yes, you're right. Sorry?
The book doesn't do it.
Yeah. I wouldn't worry about scaling the mass correctly, guys. As long as the boxes are equal, that's all you need. Yeah. And what Juho has, let me copy Juho. Juho, do I have permission to copy you? Juho, do I have permission to copy your answer? So this was 4, and this was 2?
This was 6 squares like that.
No. This was 0. And this is 6. 1, 2, 3, 4, 5, 6. And this is 2, right? Yeah.
We found one actually.
Juho found one that works. 4 squares. And then 6 squares minus 2 squares is still 4 squares. Yeah. How does the situation change if we consider... How does the situation change if we consider the system to only contain the car? If the system only contains the car, how would the situation change? Is momentum going to be conserved if the system only contains the car? It won't. Because if we're only considering the car, there's an external force applied by the truck. So therefore, momentum will not be conserved. So if you're only considering the car, you will have this and then this. And you'll experience a loss of momentum of these many units.
So, as the truck's final momentum should be equal to, with the car's final momentum should equal 0.
Should equal the car's initial momentum. Yes.
Since they are one distance.
Yes.
I was trying to, I was confused, but I was trying to see how can truck's initial momentum be the same as the final.
Oh, truck's initial momentum is 0. This is 0.
I was trying to see what can you compare.
Oh, okay. Okay, the rest of it is homework, guys.
Okay, maybe use a 1.5.
I use 1.5.